क्या कर रहे थे? We were doing entropy. ठीक है, disorder. I told you that delta S. ठीक है, just very quickly a quick revision. Okay, what is entropy? Less disorder, low entropy. This is more disorder, more entropy. ठीक है, more entropy is more stable. Uh, you got a higher probability for that. Uh, it's a more probable low energy state. High entropy is difficult. Sorry, low entropy is difficult. High entropy is the more probable one. ठीक है, the more stable, the low energy state. Uh, if you gain entropy, that's delta S positive. If you lose entropy, that's delta S negative. Then I told you about the importance of entropy, which was that if there's a lot of disorder created, a lot of useful work gets produced. So if something like water liquid turns into water gas, तो क्या होता है कि a lot of gas particles a lot of disorder would be created and the piston would start moving upwards. Same with petrol combustion engines, a lot of disorder gets created, and that's why the piston moves. Yeah. So that's one thing. Then I talked about predicting the sign of delta S, which was that if something is a solid, that's low disorder, low entropy. If it's a liquid, then it's slightly more entropy. Gas, very large increase in entropy. Okay, so the graph for water would kind of look like this. Okay, uh, I mean, if there's a change of state, that's when the disorder increases. Then I talked about okay, how do you predict the sign of delta S? That if you have a chemical reaction and if the number of gas particles they decrease, then that's negative entropy. That's a decrease in disorder. If the number of gas particles increase, that's an increase in disorder. Then I told you about if in an equation you've got the same state of particles, and you're being asked what will happen. Is there a gain of disorder? Is there a loss of disorder? So you'll just, if you have the same state, you just count the number of particles. If you had 4 particles initially, now you've got 7 particles. So that's an increase in disorder. The more particles you have, the more disorder is going to be created. ठीक है, ये सारा क्लियर है? कल इज दिस क्लियर जो कल किया था?
Yes, sir.
अच्छा, अब ये कि सर जस्ट this one. So we'll just do questions. We just want to figure out the sign. Remember, it's a very small topic. ठीक है, not that difficult. अच्छा, इसमें एक है कि किधर गया? Hold on a second. अच्छा, so what I'm going to do is we'll just do questions. एक सेकंड में लोगों को ऐड कर लूं. अच्छा, we'll just do questions where we would have to figure out the sign of delta S. ठीक है, so if you look at this equation, he's saying explain why the entropy change delta S of reaction number 1 is positive. Positive का मतलब है कि just a second. So what do you mean by delta S of a reaction is positive? There's a grain of disorder. ठीक है, can anyone explain what's the reason? Why is the disorder increasing in this reaction?
Because the number of gas particles are increasing.
ठीक है, तो शुरू में you had a solid. I mean, you had solids over here. ठीक है, in your reactants, and in your products you have a liquid and a gas. So obviously gases have a lot of disorder. So there's an increase in gas particles. Okay, that's your simple explanation, nothing complicated. So that's why your delta S is there's a higher disorder in the products, more disorder gets created. अच्छा इसी तरह के questions, similar questions. Just a second. What is meant by the entropy of a system? It simply means ये हमने बिल्कुल start के अंदर we did this. It's a measure of disorder of a system. That's about it. So it's a measure of disorder of a system. Place one take in each row of the table to show the sign of entropy delta is NaCl dissolving in water. So, what happens when NaCl dissolves in water? मतलब यहाँ पे I'll just make another point. मतलब obviously क्या होगा? Delta is positive or negative? When an ionic solid dissolves. साथ क्या होगा? Ahmed?
Positive, sir, because the number of ions increase, right? Particles increase.
ठीक है. So like if you have NaCl solid, if you dissolve it, it becomes NaCl aqueous and it dissociates. It's going to become Na+1 aqueous, and it's going to become. So one of the reasons why disorder would increase is that in solid the particles are very highly they have a regular fixed pattern in solids, while in aqueous state they're going to be randomly moving around, so there's going to be more disorder, plus the number of particles also increase because they dissociate. So that's so you have what you have is more dissociated aqueous ions, hence your delta S there's an increase in disorder, so that delta S is positive. As a next, water solidifying to, so this one was delta S positive, this one is water turning into ice, that's obviously delta S negative. Give me just a second. So this one is तो आगे चलते हैं. अच्छा, next graph. You've got अच्छा delta G, we haven't done delta G yet. ठीक है, just stick to delta S. More equations. So let's do this quickly. Liquid water at 80 is cool to 60. So what is that? That's a decrease in disorder. Particles will have less kinetic energy, and it's going to be a very minor decrease in disorder. At 80 and 60, water kind of looks exactly the same. So they're almost in the same disordered state, almost the same disordered state. But there's going to be a decrease in disorder because they have lesser kinetic energy. So the particles will be slightly less disordered. Okay. Is this clear, this one?
Yes. Yes.
So calcium chloride is added to water in the mixture stirred. So calcium chloride is soluble, so it's going to turn into dissociated aqueous ions. So the number of particles increase, and they're in a more disordered state, in an aqueous state. So delta S over here is positive. I said over here he's talking about lattice energy. What was the equation for lattice energy of calcium chloride? कि PDF stuck हो रही है. I'll just write over here. So what is lattice energy? We did this earlier. Gaseous ions. ठीक है, जिसमें we did Born-Haber cycle. So gaseous ions Gaseous ions, not solid. They would turn into, so they're going to turn into calcium chloride solid. And so there's a decrease in disorder. Okay, gases, the number of gas particles they decrease when it comes to lattice energy. ठीक है, ये भी clear है?
Yes, sir.
Yes, sir.
अच्छा, so I guess इसी तरह के simple basic questions. ठीक है, nothing really difficult about it. I mean, for example, over here he's probably going to ask you. No, he's not talking about delta S, but over here delta S is clearly positive because the number of gas particles increased. ठीक है. Okay, anyways, we're going to move on from here. ठीक है, that's predicting delta S. The next part is about calculating delta S. Okay, how do you figure out the value of delta S? So delta S is what? Entropy or disorder is what? ठीक है, we're going to try and define it. ठीक है, I explained to you ये जो example था ना कि steam engine or car engine, combustion engine, right? There was a basic concept that whenever disorder gets created, right? So when you boil water and it turns into steam, what happens? Disorder is created. What happens when the disorder gets created? The piston moves up, so work gets produced. So when you create disorder, work gets produced. When you create no disorder, work is not produced. ठीक है, for example, अगर यहाँ पे water होता ना liquid state में, if it was at let's say 10 degrees centigrade and you turn it into water at 30 degrees centigrade, so not a lot of disorder gets created. So the piston will not move as long as you have liquid water. ठीक है, so as long as disorder is not created, no work, external work is going to be produced. ठीक है, तो ये idea clear है? Is this clear to everyone? Okay, disorder is created, work gets produced. Is that clear?
Yes, sir.
Yes.
So that's the definition of entropy actually. It's the work that is going to be produced, useful work that's going to be produced by the system at a particular temperature. Okay, so the definition is for entropy changes. It's the work that's going to be produced. Work produced is exothermic, so that's why you've got a negative sign. Okay, whenever work gets produced, that's an exothermic process. So I've put a negative sign. And temperature is important because wo jo steam wala reaction, temperature is pretty important because the amount of work that's going to be produced is going to be different at a different temperature. Okay? If you're talking about water is going to produce a different amount of work if it's at 10,000 degrees centigrade. It's going to produce a lot of work at 10,000. Okay? So you have to be very specific about temperature. Water, on the other hand, will produce very little work if it's at minus 50 degrees centigrade, because it's going to be in the form of ice and it's not going to produce a lot of disorder. So that's basically the formal definition of entropy change. That's how you measure it. Okay, so we're gonna write the unit of entropy change. So it's going to be joules per Kelvin. So the temperature is always going to be in degree kelvins. This is going to be in joules. And if you're talking about standard entropy, then it's going to be per mole. So it's joules per Kelvin per. So you're calculating it for 1 mole of substance. So standard entropy or entropy changes are calculated for 1 mole of substance. So our equation for delta S is basically minus delta Q which is the work produced, divided by temperature, which is going to be in kelvins. That's it. Okay, so that's a simple formula. Disorder gets created, work gets produced. Okay, measure the amount of work that's produced at a particular temperature. Okay, clear? Is the formula clear?
Yes, sir.
Yes.
अच्छा अब होता ही है कि you don't actually use this formula. ठीक है, this formula is not going to be used very often. I mean, this is the method in which entropies are calculated. So the point is, let me add this formula is not very important. As your entropies, as entropies of products and reactants will already be given to you. They will already be provided. So, for example, you've got reactants and you've got products, and they're turning into products. So the point is that your entropy change is basically the entropies of the products would be given to you, and the entropies of your reactants would also be given to you. So all you got to do is you just have to calculate the difference. That will tell you the entropy change. So it's the entropy of the products minus the entropies of the reactants, and that's it. So this is the formula that's more useful. Okay, so we'll be more interested in so we're going to be a lot more interested in this formula. Okay. Is this clear? This formula, you got products, you got reactants, you just calculate the difference, and that's your entropy change. Is this clear?
Yes, sir.
Yes.
So again, I'm going to move to the worksheet. So let me just close a few pages. So I'm going to do questions where I would be calculating. So for example, you've got this equation. He's asking you to calculate delta S for this reaction. So you got your products. So what's the formula? It's the entropies of the products minus the entropies of the. Somebody try and do this on your calculator. So what are your products? It's Si8Cl3, which is this one. So it's 314. And H2, which is 131. So that's my product minus my reactant, which is silicon. That's 19. And the other one is HCl. So there are 3 HCl. So it's going to be 3 times 187. So what do we get for this? What's my delta S over here?
It's a negative 135.
Yes, we're getting negative 135, and the unit is joules per Kelvin per mole. Or joules per mole per Kelvin. I mean, it's the same thing. यहाँ पे it's joules per, ठीक है, it's Kelvin per mole. So that's a simple formula. And we're going to try and calculate delta S for some other reactants. As we can try and do this for this equation. We've got our products, we've got our reactants, the entropies are already given to you. So we're going to do product minus reactant to find out the difference. So what are my products? It's half N2, so it's so my product is half times what, 192 plus O2, which is half O2, so that's half times 205. plus half I2, which is half times 261. Or plus 2 H2O, so that's 70 times 2. Minus my reactant. My reactant is NH4I3, so it's minus 42. So it's plus 42. So that's my expression. So what is delta S for this? क्या आ रहा है?
427.
Because this thing is coming out to be 427. Positive, right?
Yes, sir.
And can you justify whether it's positive or not by looking at the equation? Should it be positive?
Yes.
Okay, so it's going to be positive. Why? Because
Yes, sir, because it's more in the products.
there are more gases in the products, right? Your question could be the other way around as well, that it's just entropies were given, so product minus reactants, that's it. So you got this. And sometimes what can happen is that just a second. Sometimes like this, you could get the reverse question as well, which is that delta S is already calculated for you. So you know that delta S is what? Product minus reactant, so it's 225.7. So it's the entropies of the product, which is over here as SiCl4, which is क्या value is 239 minus my reactants. So Si is given as 18.7. And the other one, Cl2, that's not given. So that's 2 times X. So you can try and calculate what the value of X is. This is the calculator. क्या आ रहा है? What's X? This is minus 239. Divided by minus 2.
223, sir.
2 to 3. ठीक है. So simple. ये भी clear है? Is this clear? Just do product minus reactants, right? Is that clear?
Yes, sir.
ठीक है. बाकियों clear? Saad, Harun, Taseem, is this clear?
Yes, sir.
अच्छा, so ठीक है. Now the next thing. ठीक है, the next thing is that इसी की continuation, which is that there's a thing called Gibbs free energy. So Gibbs free energy is that so this thing is delta G. Now Gibbs free energy is the total useful or total energy available for useful work. So a system has a certain amount of energy. If it's got excess energy, that it's giving out energy, it doesn't need energy. Negative means exothermic, right? So if the system has a lot of energy, it's giving out energy, it's producing energy, then that means it's feasible. It doesn't need, it needs, you don't, I mean, the system doesn't need any help. Vice versa, if the Gibbs free energy comes out to be positive, which means that it needs energy. That means the reaction is probably not going to happen and it's not going to be feasible. Okay. So for example, so sometimes a reaction is going to be feasible, sometimes it's not going to be feasible. Now, this is boiling water. Okay, boiling water. Do you think that's feasible or not feasible? क्या होता है boiling water? Is that feasible or not? Additional, I'll give you some information. Is boiling water at minus 100 degrees centigrade feasible or not feasible? Okay,
At negative 100, sir?
negative 100. Will you be able to boil water at negative 100?
No,
I
sir.
mean,
No, sir.
nothing would happen. It won't boil. Okay? Like if you just have a bowl of water and it's at minus 100 degrees centigrade, nothing will happen. It will turn into ice. It will probably not boil. It's not going to boil. So that means the reaction is not feasible. It doesn't have enough energy to do what you're asking it to do. Vice versa, if the same reaction, if you do it at 1000 degrees centigrade, like there's an oven which is at 1000 degrees centigrade, and you put a bowl of water into that oven, then it's going to be very feasible. Because the system has a lot of energy and it's going to release a lot of energy. So it's going to do all the work on its own. It doesn't need any help from outside. So the point is that reactions and systems, they are feasible sometimes and they're not feasible. Sometimes they have enough energy to do everything on their own. Sometimes they don't have enough energy and they won't be able to do, they would need energy. So that would make it positive. So idea clear? What, I mean, just the overall idea, like what is delta G? Is that clear?
Yes, sir.
So the point is, how do you measure, how do you figure out that the system has energy or not? So delta G is the total energy that is available to a system, right? So there are two things. Every system, we've discussed this before, every system produces work in two ways. It produces heat energy or consumes heat energy. And the second way in which it's going to do work is that it produces disorder. Because so the total energy that's available to a system is the total of both. Okay, let's go back to the example, ये जो car engine वाला example है, ठीक है? Now, burning petrol, right? What does it do? It produces a lot of heat energy. So that means the system is really, so there's a lot of heat energy produced when you burn petrol, right? Plus, there's a lot of disorder created, right? So which is why the piston moves up. Not because of the heat energy, it moves up because there's a lot of disorder that's created, right? इसका मतलब है overall this system is actually producing a lot of work, right? Because whenever you burn it, it's going to produce heat energy and it's going to produce a lot of disorder. So that means the reaction will always have, I mean, it doesn't need any help from outside. It's always going to be energetic. It's always going to be producing useful work. Plus, it's going to be producing a lot of heat energy, right? So the total Gibbs free energy of this system is always going to be exothermic. Okay? It's always going to be releasing energy. It doesn't need any help. Okay? ये वाला clear है? Is this clear? Idea clear? Okay, how does the system produce energy? Is this clear? Asina, is this clear? Ahmed, Saad?
Yes.
Yes.
Yeah.
Okay, so Asaf, on the other hand, what about the steam engine one? The steam engine one, it actually needs heat energy. Okay, it's an endothermic process, right? So water liquid turning into water gas, that won't happen unless you give it energy, right? But at the same time, it's producing work produced. Why? Because when steam gets produced, a lot of disorder gets created and work gets produced. The piston gets pushed upwards. So now this reaction is actually not going to be feasible at lower temperatures. I mean, even apart, it will produce work, but at lower temperature, it would need a lot of heat energy so that it could turn water liquid into water gas. So this piston is not going to move at a lower temperature. That thing will work at a lower temperature, but this will not work at lower temperatures. But this will work at higher temperatures because it needs energy, so it will get that energy, and then it's going to produce work, right? So overall, it's going to be a lot more feasible if you do it at a higher temperature. ठीक है? So different types of reactions होते हैं. So we're going to come back to this part, that every system produces heat, which is what? Which is delta H. And every system produces work which is due to disorder, not produces disorder, produces work which is due to disorder. अच्छा, उसका तो formula delta H है, right? Every reaction has a certain enthalpy change, endothermic or exothermic, so you can determine the heat produced. Lekin what about, how do you predict the work that's going to be produced due to disorder? We already wrote down a formula earlier. ये वाला formula. Formula क्या था? What was entropy change? Entropy change was the work that is produced at a particular temperature, right? So it was delta S was basically minus delta Q over T. So we've learned how to calculate delta S. What we can do is we can just rearrange it. So the work that is going to be produced is basically what? It's T times delta S with a minus sign. So this over here is the work So ये clear है कि how do you measure the work produced due to entropy change? Is this clear?
Yes, sir.
Yes.
ठीक है, तो I just rearranged the formula for delta S and I got the formula for work produced due to delta S. So I'm just going to put it over here. So what I'm getting over here is okay, my delta Q is what? It's minus T times delta S. So I'm going to put the two terms together. So what is delta G? Delta G is basically the sum of the two things. So it's basically delta H, heat energy produced, and the work that is produced due to entropy change. So that's minus T times delta S. So that's my formula for Gibbs free energy. Okay, so it's basically made up of two terms. एक ये, and one of them is this one. So clear this, I mean, this is the last formula actually. So is this clear? Okay, what is delta G? ये सारों को clear ना?
Yes.
Yes.
Achha, so the only thing to be careful about is that the unit for delta S is actually joules per Kelvin per mole. The unit for temperature is always going to be kelvins. And the unit for delta H is kilojoules per mole. And the unit for delta G is actually kilojoules per mole. So your T wala part hai, that gets cancelled out because the Kelvin over here cancels out with the Kelvin over here. So you still, I mean, this thing is basically joules per mole. The only issue is that some of the terms are calculated in kilojoules, the other ones are calculated, I mean, entropy is calculated in joules. So you have to keep the units consistent. Which basically means that you either use kilojoules everywhere or joules. So if your entropy is being calculated in joules, ठीक है, यहाँ पे check करो in these questions. Every time when it comes to entropy is in joules. But every time when you see this other stuff, so every time when you see enthalpy change, that's in kilojoules. So yeah, you either have to work in kilojoules or you would have to work in joules. So make sure you convert the values either in all of them in joules or all of them in kilojoules. ठीक है? ये mixed काम नहीं चल सकता, ठीक है? You can't work with that. So make sure you do this. When you use this formula, make sure you make the units consistent. So now that's your delta G. So using this delta G, if this delta G comes out to be negative, that means it's feasible. Exothermic, if it comes out to be positive, that means it's not feasible. Now you're going to get two types of questions on this. It's either going to be quantitative, where you would be asked to calculate values. वो आपको temperature, they'll be giving it to you. Delta S, we've already learned how to calculate. Delta H would be given. So you can just calculate, put in the values, and you can find delta G. The other one is, so then there's going to be some qualitative questions, which is guesswork. So this one is basically predicting the sign of delta G. Are you going to get exothermic or are you going to get endothermic? So for example, example number one, water liquid turning into water gas. So this example, when I just want to figure out whether this reaction, when is this reaction feasible? Higher temperature or lower temperature, right? Now, this is an obvious reaction. We know it's feasible at higher temperatures. We know that it's exactly feasible at 100 degrees centigrade and above temperatures either or above 100 degrees centigrade. It doesn't work at below 100, or it becomes very unfeasible below 100. Below zero, it's going to be impossible to happen. Anyway, so how do we incorporate the Gibbs free energy in this question? So iski enthalpy change kya hai? Can anyone tell me, is this endothermic or exothermic? I mean, without any values, what's the sign? Positive or negative?
Is it endo?
Okay, so this one is clearly endo. And can anyone tell me what's the sign of delta S over here? Positive or negative?
Positive, sir.
Okay, so this one is, there's an increase in disorder. So this one is positive as well. Now what we're going to do is, I've got the Gibbs free energy formula. I know that this reaction is feasible at higher temperatures, right? I just want to prove it using the Gibbs free energy formula. So delta G is what? It's equal to delta H minus T delta S, right? So what happens? My delta H is coming out to be what? Positive. And my delta S is coming out to be positive as well. Now in this way, because of the negative sign over here, this entire term actually becomes negative. So I've got two things. I've got two terms. I've got one term which is positive, and I've got the other term which is the exothermic term. So when is Gibbs free energy exothermic? So when is delta G going to be less than zero or negative? It can only be less than zero if the first term is small, the positive term is small, and the negative term happens to be large. So if I keep the negative term large, that means in that scenario, delta G will come out to be less than zero, or it will come out to be negative. If the negative term is bigger in size and the positive term is smaller in size, okay? So the idea clear that I would want to keep this large, so I get a negative delta G. Is that part clear? Iski jo math is that clear?
Yes.
Yes, sir.
So there's only one variable over here, which is temperature. The other ones are kind of fixed. Enthalpy change and entropy changes are kind of fixed. So if you want to make this term large, the negative term larger, you need to have a larger or higher temperature. So this kind of indicates that the reaction will be feasible if you keep things at a higher temperature, which is, we already know that this reaction happens at higher temperatures. The higher the temperature, the more negative this term over here will become. And the higher the temperature, the more negative delta G you're going to get. So which would mean that the reaction is very feasible if the temperature is kept as high as possible. And it's not going to be feasible at lower temperatures. If you keep a very low temperature, तो आपका जो delta S वाला part है, that becomes very small. The negative part becomes very small. So overall your delta G will come out to be positive because enthalpy change is positive. ठीक है? So is this idea clear that when is this reaction feasible and how did we determine using the Gibbs free energy? Is that part clear?
Yes.
Yes.
So this is a example. Let's say I've got water liquid and I'm trying to turn it into ice. So obviously I know, I mean, these are the reactions I already know. I know that this reaction is feasible at higher temperature, lower temperature.
Lower temperature.
So if I want to make ice, I need to have a lower temperature, feasible at lower temperature, right? इसका मतलब at lower temperature, your delta G will come out to be negative. It's going to come out to be less than 0, right? So I'm just going to prove the same thing using Gibbs free energy. So iska kya hai? What is delta H for this? It's when liquid turns to solid, that's exothermic. And what's the delta S for this disorder? It's also negative, right? Come on, you had a liquid and that liquid is now turning into a solid. So it's decreasing, right? So what was delta G is equal to delta H minus T times delta S. Now in this question, the delta H part is negative and the delta S part is also negative. But since you got two negative terms, this side would actually become positive. So you got a positive term, you got a negative term. Now, if I want to make delta G negative, right? I need to have the negative term larger. I need to keep the positive term smaller. And there's only one variable, which is temperature. So what I'm going to do is I'm going to keep T as small as possible. I'm going to try and keep T as small as possible. So delta G will come out to be less than 0 if T is small. Already discussed what making ice happens at a lower temperature, right? So is this clear that by just using the Gibbs free energy without any values, I was able to predict when will the reaction become spontaneous or feasible? TK, clear? Is this thing clear? This one, both examples.
Yes. Yes.
So you can now kind of apply it to any other equation. You get the same concept. You just apply it, and so we'll do that in the next class. You will do that tomorrow. Yeah, how to predict when reactions would become spontaneous or feasible and when they're not going to become spontaneous or feasible. So the other part is easy. If they give you values, then it's pretty easy. You just plug in the values, that's it. You get the value of delta G. Negative, so that's feasible. If it's positive, that means it needs energy. It's not going to work. So if the values are given, then it's easy, just plug in the values. Okay. So chalo ye kal karte hain. This was the last part. Okay. So we're actually done with entropy as well. We're going to try and do questions on entropy. वो कल करते हैं, ठीक है? इसको भी थोड़ा सा और डिस्कस कर लेंगे. चल ठीक है, कल बात होती है. I've shared the folder link with you, ठीक है, which has the videos. ठीक है?
Okay, sir. Thank you.
Okay, everyone, take care.